Section 9.3, Fluids in Motion. The objectives here are to discuss the motion of a fluid using the continuity equation, to recognize the effects of Bernoulli's principle on fluid motion, and to differentiate between turbulent and laminar flow. So first, let's discuss some definitions that are needed here. Laminar. Laminar means that all points in the fluid flow on the same smooth, predictable path. And you see laminar flow if you just turn on your faucet and the water leaks out nice and slowly. Turbulent flow exists when there's irregular, unpredictable fluid flow. And turbulent flow, a good example, if you ever look at like a river or like whitewater rafting, and you see like all the eddy currents, you see all the white water coming about because of the turbulent flow that's producing it. The third term is viscosity. Viscosity is the amount of internal friction within a fluid. An easy example to think about is like water versus maple syrup. Maple syrup is very viscous compared to water, which is not very viscous. It flows much differently and much slower. An ideal fluid is the final definition, and an ideal fluid is what we're going to be working with in this section. An ideal fluid is something that is incompressible, non-viscous, and non-turbulent. So pretty much a very plain, simple fluid flow. Okay, if the fluid itself could be compressed in a container, then it would not be ideal. If it's very viscous, it wouldn't flow with those properties. If the flow is turbulent, it would not exhibit these properties. So we're going to be looking at ideal fluid flow. Now there's a measurement known as the Reynolds number, Reynolds number, that is a dimensionless quantity. It determines whether the fluid flow is laminar or turbulent. It takes into consideration things like density, velocity, diameter of the piping. So there are different parameters that affect Reynolds number, but if the Reynolds number is above a certain limit, it is considered to be turbulent flow. If it's below that limit or that threshold, it's considered to be laminar flow. Let's start with the continuity equation, which tells us that a fluid flowing in a pipe has a constant volumetric flow rate. Volumetric flow rate. That means that the same volume flows through the pipe at the same rate. Okay, the same amount comes out of the pipe at the same time or the same given period. Now, what's interesting to see is that most people make a misconception here. Okay, and what they'll realize here is that V1 is actually traveling faster, okay, than V2. The reason is because the same amount of volume has to get through this little area of pipe in the same amount of time because it's being pushed along. So it's going to move faster to make up for that, whereas this is a wider pipe, it can move slower, although the same volume is still flowing through. Okay? Now for a fluid flowing in a tapered pipe, like a pipe with a variable cross-section, the speed is faster when the pipe is narrow, and it's slower when the pipe is wide, like a fire hose. A fire hose, you can adjust the nozzle at the end of it. So the fire hose might be some rubber hose, and then suddenly at the end, there's this nozzle at the end of the fire hose. And the cross-sectional area, this can be rotated. And what happens is it adjusts the opening at the end of the hose. And if you close the opening a little bit, the water will travel further, and it'll be able to reach higher windows, as opposed to when the opening is made larger as an opening, it does not travel as far because the velocity is less. And we know from projectile motion, initial velocity really indicates how far something will travel. A good example of this as well is to think about if you're ever watering a garden and you need to reach a further part in the garden, you could put your thumb over the end of the hose if you don't have a sprayer. You put your thumb over the end and the water goes further. Well, that's because you're reducing the area. Okay, if I reduce this area here and yet this value is held constant, it means that the velocity has to go up. So if I have the area, it means that the velocity will double as a result. Example 1. Water is flowing through a pipe that has a radius of 4 centimeters with a velocity of 5 meters per second. What should the radius reduce to for the velocity to double? So we start right away by seeing that the initial radius in this problem is going to be 4 centimeters, which is just 0.004 meters. And then we say that the initial velocity here is 5 meters per second. We are trying to figure out what the second velocity will be, what the second radius will be. We know that the second velocity is double the first velocity, or simply 10 meters per second. And we're trying to figure out what the second radius should be, what it should reduce to. And it says reduce, but we should know it has to reduce, because for something to speed up, it has to have a smaller radius. Now remember, in this problem, we're trying to have the velocity double. We could say right away that the cross-sectional area just has to halve. And that's again from the continuity equation we're going to write here. Okay, so for the continuity equation to hold true, If you double the velocity, you'd have to have the area on that side. But we're not looking for the area, we're looking for the radius, so it's going to be a little bit different, and we'll make a conclusion at the end about why that's different and how. So the first area, we know it's a circular pipe here, right? So it's pi r1 squared. V1 equals pi r2 squared V2. Cancel pi's on both sides, and we're looking for r2. So r1 squared V1 all over V2. And so we get rid of that by dividing by V2. And then we take the square root of the answer. And that gives us r2. Okay, so we square root it and we get r2 by itself. Now what we can do is we can plug out our numbers, or we can also notice the following. If I realize that V2 is just double V1, I can replace this with double V1. And then what happens is the V1s cancel, which tells us that the second radius is simply a result of the square root of r1 squared over 2, or just r1 over root 2. Okay, again we get r1 because it's the square root of r1 squared. The r1 squared part and the square root cancel one another. So we have r1 over radical 2. So what this means is that the second radius reduces by what factor? By a factor of radical 2, not by a factor of 2, like the area would reduce by. So anyway, let's plug in numbers. Okay, we can either go back up to this stage and plug in numbers here before we plugged in the 2v1, or plug them in down here at the bottom and see. And do that, and I'm plugging my radius at 4 centimeters, which is 0.04 meters over radical 2. It gives me r2. Which ends up equaling 0.028 meters. And this just becomes 2.8 centimeters, really. And I just realized at the top, this should be moved over right there, so make sure you make that change. Next, we'll take a look at Bernoulli's principle, which states that the pressure in a fluid decreases as the fluid's velocity increases. Okay, so we're seeing here, if we remember the continuity equation, the velocity is clearly increasing in this region, because it's bottlenecking, and from the continuity equation we can see that. But here we're going to see that when there's increased velocity, it looks like the pressure went from a higher pressure to a lower pressure here. So the reason is this is because for the velocity to actually increase through this bottleneck, there has to be an acceleration, and if there's an acceleration, it means there's an unbalanced force. So there's some F net, and if there's F net, then there's some pressure differential. So the pressure here is like it's all getting backed up like a traffic jam. So there's a lot of pressure here, but then once it gets through, it's able to move out easily, so it's a lower pressure region here. Next is an application of this, which is an airplane wing. We can see here is that the force on the wing is explained using Bernoulli's principle. So the wings are designed so that the speed above the wing is faster than the speed below. So you have high speed up here and low speed down here. Well, if there's lower speed down here, what happens is it creates a pressure differential. Okay, so the pressure above the wing is less than the pressure below the wing. So here's low pressure, high speed. Here's low speed, high pressure. If there's higher pressure here and there's lower pressure here, it's going to naturally push up from the higher pressure to lower pressure, so you're going to feel this force of lift. And if this lift force is greater than the drag force on the airplane, then the plane will lift off.